I want to talk about one more thing this week, and that involves eigenvalues and similar matrices. So recall that if we have two similar matrices, A and B, that means there exists a matrix Q that's invertible, and you can write A is equal to Q inverse B times Q. Well, I want to see if there's some kind of relationship between the eigenvalues of A and B. So what I'm going to do is I'm going to subtract from A lambda times I, because that's how we begin to find the eigenvalues. So since A is equal to Q inverse B times Q, I can subtract lambda I from the right-hand side as well. Now remember that the identity matrix, if you multiply the identity matrix with anything, you get what the C here. So if I take I and multiply it by C, I get C. And it also works if I multiply on the left by C, I get C. And the reason I'm bringing this up is, what happens if I multiply this? Well, I times Q is just Q, and then Q inverse times Q is I, or I could do Q inverse times I is Q inverse and get Q inverse Q. Any way that I multiply these, I just get the identity matrix. So where I have this identity matrix, I can substitute this because the identity is equal to that. So now we have that A minus lambda I is equal to Q inverse BQ, subtract Q inverse lambda IQ. Now lambda is just a scalar, so it can come out, and you can see that we just get lambda times I. The next thing I want to do is I kind of want to factor out this Q inverse from the front and this Q inverse from the back. So you can see that A minus lambda I is equal to Q inverse times B minus lambda I times Q. Well, to find the eigenvalues of A, I take the determinant of this matrix. But since these matrices are equal, well, I can take the determinant of this matrix. Okay, so you can see that these determinants are equal, but we have this special property of determinants. It says if I have matrices being multiplied together and I'm taking the determinant, well, I can just take the determinant of each matrix and multiply them together. But the determinant of a matrix's inverse is 1 over that determinant of the matrix. And these are just real numbers, so we can move them around, and these cancel. So we can see that the determinant of A minus lambda I is equal to the determinant of B minus lambda I. What does that tell us? Well, if A and B are similar, then they have the same eigenvalues. Okay, something I want to stress is that if two matrices have the same eigenvalues, that does not mean they're similar. Okay, it's if they're similar, then they have the same eigenvalues. Why is this important? Well, it can help us with some calculations, particularly if A is similar to a diagonal matrix. So, if A is similar to a diagonal matrix, D, then they have the same eigenvalues, but remember how you take the determinant of the matrix D. Because it's diagonal, it's just the product of the diagonal entries. So if it's the product of the diagonal entries, then what happens is the diagonal is actually just equal to the eigenvalues. So for example, let's say A is an n by n matrix. Let's actually be more specific. Let's say it's 5 by 5. And let's say it has the characteristic polynomial lambda minus 3, lambda minus 2, lambda plus 4, lambda minus 1. And let's remember that it has to be an nth degree polynomial because this is a 5 by 5 matrix. And that means we could have either 5 distinct eigenvalues, and if that was true, the powers on each one of these would be 1. Or we could have less, but the multiplicities have to be bigger than 1. So let's do something like this. Now suppose A is similar to a diagonal matrix. Okay. Well then A is Q inverse DQ, where D is going to look something like this. 3, 2, -4, -4, 1. Actually, these eigenvalues, they might be in a different, like you could permute them, maybe put a -4 here, a 3 here, a 1, a 2, a -4. But they're going to have the eigenvalues along the diagonal. So the question is, when is it actually similar to a diagonal matrix? If the eigenspaces, the basis vectors, are linearly independent, then A is actually diagonalizable. So if you had a 1 for each one of these, let's say you had 5 eigenvalues, then you could put the 5 eigenvalues here, and then A would be diagonalizable. You would be able to find the similar matrix with just the eigenvalues. Now, if we have higher powers like this, then the matrix may not be diagonalizable, meaning you might not be able to find this diagonal matrix that it's similar to. It's only true if the basis for all the eigenvectors, if they're linearly independent and they form a basis for your whole space, which here would be C5, right? So you have to be careful. But definitely, if all of these have a power 1, the eigenvectors, remember that the algebraic multiplicity here is 1, and the geometric multiplicity will have to be 1 as well. And the eigenvectors will form a basis for your space, which tells us that we can write, we can find a basis. So you can find a basis. So let's say you have 5 eigenvalues. So lambda 1, lambda 2. Let me erase this. So let's say you had 5 eigenvalues that were distinct. And each one of these eigenvalues had one thing in their basis. So V1, V2, V3, V4, V5. And if V1, V2 to V5 is actually a basis for your space, then it's diagonalizable. You can find a diagonal matrix, and all you have to do is just put the eigenvalues here. We'll talk about this more next time, but why would we want to do something like this? Why is this important? Well, if you want to take a matrix and raise it to some power, and you have a diagonal matrix that it's similar to and you want to raise it to a power, well, remember that this is just equal to Q inverse d to the mq. So if this is really complicated to figure out, this isn't, because a diagonal matrix, if you square a diagonal matrix, you just square the diagonal. If you raise it to a really big power, let's say to the power 10 or 100, then you just raise the individual diagonal entries to the power 10 or 100. And so the calculation is a lot quicker. Once you find this diagonal matrix, you just multiply it by Q inverse and Q, and then you get the matrix you want. So that should be able to help you. So if you're able to find this diagonal matrix, which you should be able to find involving your project using your eigenvalues, you should be able to find a basis that goes with those eigenvalues, and then you'll be able to raise this matrix to a high power.